Welcome back to chapter 23. This should be the fourth video. The third video left off with us talking about the bell curve and directional selection. And I'd like to recap with you really quick. To start with, the bell curve shows that for any given trait, most people are just average for that given trait, whether that be height or hair color or an eye color or length of a finger or what have you. Most people, for every trait, there is an average. There are some people that are much higher than the average. If we're looking at height, you could think of Shaquille O'Neal, 7-footer. Most people are not 7 feet tall, but a few people are. And then you might have some really, really short people. Not many people are really, really short, but some people are. For any trait, height included, most people are right near the average. So we talked about the three different things that could occur to that bell curve when one of those groups of people have an advantage. And those three things would be directional selection, stabilizing selection, or disruptive selection. To recap directional selection, our average is right here, but what would happen if the people right here had a selective advantage? Well, they're going to have a higher level of fitness, and as a result of that higher level of fitness, the number of people right here will increase. And as a result of there being more people that have this selected trait, maybe it's height, this average will start to increase, and the average will shift in that direction. Over the course of time, provided that these people continue to have a selective advantage over the average or the below average people, this becomes the new norm in the population, and this is where the new average would be established. What would happen as a result? Well, our bell curve, which was right here, shifts over to favor the people that have the advantage, and our bell curve would now be over here. That is directional selection. In this sample, I showed the above average individuals having the advantage and it moving to the right, but it could be the exact opposite. If the below average people had an advantage, it could shift this way as well. The next example is stabilizing selection. Once again, in this image, we see that most individuals are average for any given trait. The example I'm going to use for this is the size of a baby at birth. Now, most babies that are born are right around 8 pounds or so. That is about the average. However, you might have some babies that are born and they're like, I don't know, we'll say 13-pound eggs, really, really big. And you'll have some babies that are born that are, we'll say 3 pounds, so very, very light. What would happen in that situation? Well, let's not think about this situation with modern medicine. So picture you don't really have doctors that can perform cesarean sections to remove babies. What are the odds of that 13-pound baby being safely born? Well, considering where that baby has to fit out of, that large baby could very well not only die in the process of being born, but it actually could kill the mother if it's too large for the mother to give birth to. So these individuals have a low chance at survival. Likewise over here, 3-pound babies, they're very underdeveloped. They have a very low chance of survival as well, especially when we don't have machines to hook them up to keep them alive while they continue to grow and develop. What we see is pressure being put on the average, and those are the ones that are able to survive better than the people that are really heavy or really small at birth. What we would see is our bell curve start to narrow in or pinch in a little bit more, and this would be the new bell curve. Notice that it's pinched in from where it currently was. Are there still some babies that are heavier than the average? Yes, but instead of being maybe 13 pounds, maybe they're like 9 pounds. And on this sense, that maybe being 3 pounds, maybe they're like 6 or 7 pounds. Those is how selection would act against traits like that, and that would be stabilizing. In other words, here's the average. We're going to concentrate on that average and hold it there. That's stabilizing selection. And the last is disruptive selection. This would happen, let's use birds and their beaks for this particular example here. Let's suppose we have small beaks, medium beaks, large beaks, and something in that environment changes that does not favor the average beak length. Maybe all that's left is really, really tiny seeds and really, really large seeds. Well, if there's tiny seeds, the birds with small beaks, they have a bunch of food that they can eat, so they'll have a lot of food. What will happen? Well, they'll have an increased level of fitness. They will increase in number. The birds with large beaks, well, if there's large seeds, they have plenty of food that they can eat, so they will increase in number as well. What would happen to the bird with the average size beaks? Well, there's a couple ways we can think about this. First off, if they have an average size beak, that's still going to be probably a little bit too small to crack open the really large seeds. So they won't be able to eat the large seeds. What about the small seeds? Well, they might be able to eat the small seeds, but what if the small seed requires that these birds eat a whole bunch of them just to meet their caloric needs? What if there's not enough energy in those small seeds for these birds and all they do is eat? Well, they might not get enough food. As a result, what would happen to this group of individuals? They would decrease as a result of the reduced level of fitness. How would our new graph look? Well, it looks something like this. An increase there, a decrease in the middle, and an increase over here, and our new graph would look something like that. What that shows us is we have two averages starting to form, and our original average is starting to go away. What could happen if these individuals were gone completely? Well, we would have a graph that would end right there, and another graph that would end right there. What would result if we had two separate bell curves? Well, now you got two different species. So speciation can occur as a result of disruptive selection. Moving on, we're going to be looking at adaptations and the role they play in survival. To start with, an adaptation is something that can be inherited from a parent, and it helps individuals survive, so it increases fitness. Right here we're looking at an adaptation in the bones of birds specifically. Now if you're looking at these two bones, which one would be of a human bone, which one would be of a bird? Well, based on what I'm seeing that the outer part of this bone is really, really thick, and the outer part of this bone is really, really thin. Well, how will that affect weight? This will be really lightweight. This will, well, it looks hollow in the middle, so it'll still be relatively lightweight, but this bone will definitely be heavier than this bone. This is the bone of a human, this is the bone of a bird, and birds do have hollow bones. How does that adaptation help them survive? Well, it allows them to fly. That's how birds move around. A lot of courtship occurs while in flight, or the ability to find mates. So birds do need that adaptation to survive at this point in their evolutionary progress. Humans, we don't have that adaptation because we don't really need to fly. So we kind of discussed this one with our stabilizing, disruptive, and directional selections. Certain features within the population, variations, can be favored. And if they are favored, and if they are heritable, then we're going to see an increase in allele frequencies towards that favored trait. And we saw that going on with directional, stabilizing, and disruptive selection. What caused people who are above average to become more common in the population? Well, a change in allele frequencies. There was more of the allele causing increased height in the population over the course of time. So there's just a few more things we have left to talk about in Chapter 23. One is being sexual selection. This will take a few slides here. Sexual selection is a form of selection where individuals with certain inherited characteristics are more likely to obtain mates. So in other words, they have an increased chance at having offspring. And as a result of having an increased chance of having offspring, there will be more individuals in the next generation that have their inherited characteristics. So let's look at a couple examples, the first being of sexual dimorphism. Sexual dimorphism is simply talking about where one species has two organisms that look entirely different from one another, such as the case here with these ducks. The males have the colored head and the lighter colored body, and females are a brownish pattern color. And another example of sexual dimorphism would be with spiders, whereas the female is really, really large and the male is really, really tiny. They do look like entirely different species, but they actually are the same species. One of the cooler examples I heard of maybe 3 or 4 years ago at this point is from a deep sea fish called the anglerfish. And the anglerfish lives in an aquatic zone that is completely dark. There's no sunlight, but it has this little lure that extends off the top of its head, and it lights up. Well, that attracts potential predators, and the anglerfish has these ghastly looking teeth that it will just, I don't want to get bit by it. Let's just put it that way. It looks like a deep sea piranha. Well, anyhow, scientists caught one of those, and they noticed that a bunch of parasite-looking things were attached to the anglerfish. And it took them quite a few decades to figure out that those parasitic-looking things were actually a bunch of males that had attached to the female. So in some cases of sexual dimorphism, they don't even look like they would be the same species at all. Such as the case with that anglerfish, but in closer inspection they actually are. So sexual dimorphism, males and females look entirely different from one another, and that's used more or less for attraction. We'll pick up with the rest of this lecture in the next video here.